Today we're going to talk about joint vibration analysis by bioresearch, a 3-minute non-invasive, accurate, and objective test of the vibrations that come from the temporomandibular joints. When temporomandibular joints are functioning normally, they're well lubricated and their action is very smooth, creates no vibration. Any pathology of the TM joints will create a vibration. And what we found is that each pathology creates a unique vibration signature. This can be used as a diagnostic aid in looking at the jaw joint. Now it's very simple to do. What we do is we place a sensor over the temporomandibular joints, measure the patient's maximum opening, and we enter that into the computer. We then look to see if at maximum opening, if the patient's jaw is deflected to the left or to the right. If it is, we enter that measurement as well. Then we have the patient open and close in time with an animation on the screen. They do this for about 10 seconds, and then we accept the trace. The vibrations from the right joint are at the top of the screen, and the vibrations from the left joint are at the bottom of the screen. The green sine wave is the opening and closing movement of the jaw in time with the animation. Here we have a normal temporomandibular joint opening and closing. You'll notice that the disc is in the correct position, and as the condyle rotates and translates down the eminence, it's a very smooth, well-lubricated movement that is not going to create any vibrations. When a patient has this scenario in their TM joints, the JVA Trace shows no vibrations during opening and closing, and only the teeth hitting at each green peak where their teeth are coming together. Now in this scenario, we have an anterior displacement of the disc, where the disc reduces on opening and then displaces on closing. You can see how this scenario would create a vibration during open and close. Now, not only does it create a very unique waveform so we can tell exactly what's happening within the joint, but as a screening tool, it's very easy to differentiate the normal trace that we just looked at to an abnormal trace because of the presence of all the vibrations, in this case, on the right and left during opening and closing. This can be used so that the staff member can triage a case very easily. Here's another example of a disc displacement, except that this time the disc is displaced medially. So when the patient closes, the disc displaces, the patient begins to open, and it normalizes or reduces to the correct position. This medial displacement also has a unique signature that differentiates it not only from normal, but from anterior disc displacement. Another example is a bone-on-bone vibration. You'll notice in the waveform in the black screen, we see a long duration and very horizontally compressed vibration, which is indicative of bone rubbing on bone. So we can use joint vibration analysis right in the office, time and time again. When we're looking at the diagnostic modalities that have been used in the past, the subjective things like patient report, palpation, Doppler, etc., we see that they have a very low accuracy of less than 50%. What's worse is that clinicians don't agree when they use these subjective measures. They don't hear the same thing, they don't feel the same thing, so the interclinician agreement's very low. When you look at the research on joint vibration analysis, not only is the normal, not normal accuracy very high, but accuracy for specific pathologies is very high. It's because we're looking at this objectively or numerically. What we do is we have a flow chart that will break joint vibrations down based on their total integral or power, by their frequency, by the patient's range of motion, and then finally you can take a look at the waveform examples at the bottom of each flow chart and determine, does that look like the trace that you're actually looking at. So what we'll do is we'll take the numbers that are given to us when we mark a vibration, its amplitude, its duration, its frequency, and plug that into the flow chart to give us a classification of the joint. This can be done before treatment. This can be done as a yearly screening. This can be done to test the efficacy of the treatments that we apply. Now, JVA is only made by bioresearch, and there's only one system in the world. There have been several other companies that have made similar devices like sonography devices, but only JVA records in Paschals, which is newtons per square meter. It's the actual pressure wave measurement of that vibration that comes through. The reason we bring up ESG is the systems look the same, and while ESG systems are more from the 70s and 80s, they do get confused. An ESG, or sonography sensor, is a microphone behind a plastic membrane. All right? JVA is actually a vibration transducer that's buried in silicone, and this is actually critical to its design. What happens is, when a vibration occurs and travels through the dense flesh, it has to, for a sonography sensor, vibrate the membrane to vibrate the air to make it get it to the microphone, and a lot of pressure is lost. So we miss those subtle vibrations in early pathology. Whereas with the JVA sensor, the silicone transmits vibration very well. So the minute movements of fluid or disc transfer very well as pressure waves to the sensor, and we can pick that up, making JVA very, very sensitive. Now, even though it's sensitive, the microphone of sonography will record room sounds, because that's what a microphone is designed to do. The phone rings, things like that. That gets picked up by a sonography sensor. But despite the fact that JVA is very sensitive to the sounds from the joint, airborne sounds bounce off the hard silicone and are not recorded. So we're very sensitive to what we want to hear, but not sensitive to the artifacts in the surrounding environment. In short, JVA provides an instant, objective, and economically friendly way for you to objectively look at the health of your patient's stomatognathic system.